Welcome back. Today we're going to take a look at area under a curve, specifically a method for estimating area that we call Riemann sums. Riemann was a German mathematician who developed an area to evaluate areas under a curve by partitioning the domain of the graph into intervals of length delta x. Notice we're looking at delta x, like the change in x. In the following example, we're going to discuss Riemann's method to approximate the area under a curve. This is on the AP. Riemann is huge on the AP. So we're going to estimate the area bounded by the graphs of y equals x squared plus 1 and the x-axis between 0 and 2 by partitioning, it should be by portioning or portion, I guess, the area into 4 parts using rectangles. Anytime we really talk about Riemann, we're looking at rectangles. So notice we're looking at the area of a parabola. And I picked a parabola for a reason, because there's no formula from geometry to find the area under a parabola. Now, when they say into 4 parts, they're telling us how many rectangles we're going to use, the number of rectangles. Now, when you look in books, there's a lot of different formulas for doing this, but I don't like to look at those formulas. I just like to say, you know what, let's go ahead and do this. Now, the first thing we're going to look at is something that we call the left-hand sum. There's 2 different ways we can look at these. One is what we have what's called the left-hand sum. And what this means is if I partition the domain 0 to 2 into 4 different regions, into 4 different equal lengths, for example, there's one in the middle, here's 1/2, and here is, of course, 3/2, or 1.5. Notice I'm going to get 4 different regions right here. What we're looking at with the left-hand sum is we're looking in the first region, and the second, and the third, and the fourth region, we're looking at the length on the left-hand side to give us the height. So what we're really kind of saying is we are going to pick the number on the left. So, in other words, between 0 and 1, we're going to find the height at 0. Now, because we're using rectangles, we're going to tell the AP about this. We are going to say that the length down here, which is going to be the change in x, which we're going to call delta x, which, notice, each one of these has the same length, 1/2. But then we have to get the height of that rectangle. Well, how do we get the height of this rectangle? Well, again, that comes from the left-hand sum. Of the 0 and the 1/2, we're going to pick the one on the left. So we're going to find the value of the function at 0. So to get the height of our rectangle, we're looking at the value of our function. So, for example, between 0 and 1/2, I'm looking at this rectangle in here. And I'm going to draw my rectangle. Notice that. I draw my rectangle. So to get the area, this is a rectangle. We know the rectangle length times width. Well, the length of my rectangle is going to be f of x. The width of my rectangle is going to be delta x. This should look a little familiar. We'll talk a little bit more about this tomorrow, okay? But one thing you want to have is you need to have this. AP says, how did you get the area? Well, I'm using my length times my width. You want this, okay? And then we're going to find the area. Well, since I'm using the left-hand sum to get my area, I'm going to look at the, between 0 and 1/2, I'm going to look at the value at 0 times the width. Well, what's the width is just 1/2 plus, next, between 1/2 and 1, well, which one is on the left? Well, that's the 1/2. So at 1/2, I find the height there, and then make my new rectangle. So that's going to be the value of the function at 1/2 times its width, which is also 1/2, plus, and I have another rectangle between 1 and 3/2. I'm going to find the height of that rectangle, which is going to be the value at 1, f of 1, times its width, which is also 1/2, plus, and then I got this last rectangle right here. which I'm going to use 3 halves because 3 halves is on the left between 3 halves and 2. So the value at 3 halves times its width, which is also 1 half. Now you can factor out the 1 half. I don't encourage that because here we're lucky they all have the same width. A lot of times on the AP they won't, so I wouldn't encourage you to factor out the 1 half. So, but now I'm just going to find the value at 0. I just plug it into my function. 0 squared plus 1 is 1 times 1 half plus f of 1 half, that is 1/4 plus 1, which is 5/4 times 1 half, plus f of 1, well 1 squared is 1, 1 plus 1 is 2, 2 times 1 half. Now 3 halves, that's 9/4 plus 1, which becomes 13/4 times 1 half. And you leave this. AP's okay with that. Just leave it alone. Although, if you're like, man, you don't know where I come from, my parents make me simplify, you would get 15/4. Now, that's my estimated area. Let me ask you a question. Would this be an overestimate or an underestimate? And you can easily tell that this would be an underestimate. But let's talk about why. Recall from last unit, anytime we talk about underestimates or overestimates, we're really looking at the curvature of our graph. So the reason why this is an underestimate, there's actually 2 reasons. One, this is a left-hand sum, and the function is increasing. Now we're going to talk more about later on what's going to be the reason, how we can tell overestimate or underestimate, but that's going to be the reason for this one right here. It's a left-hand sum and the function is increasing. We're going to take a look at a bunch of those. There's 4 different ways this can occur for underestimate and overestimate. We're going to discuss them in just a few moments. Alright, but now let's get the area using what's called the right-hand sum. So again, I'm going to partition this up into 4 equal rectangles, 1 half, and there's of course 3 halves. But this time I want the right-hand rule. So instead of picking the x value on the left, I'm now going to pick the x value on the right. So we're going to pick the number on the right this time. So again, I'm going to write out how am I going to get this. There's my right. There's my right side. Between 1 half and 3 halves, I picked the number on the right. I can see my rectangles between 3 halves and 2. I draw my rectangles. AP loves to see this. AP loves this. They love to see where you got your work from. Now remember, each delta x is a half a unit long, and we're going to get the height by looking at the value of the function there. So we're going to write that down. Area equals f of x delta x. You need this step. You're telling the AP you're looking at rectangles right here. And you're going to see a very important use for this tomorrow, in tomorrow's lesson. Alright, so we're going to look this time at the right side. So to get my area, I look at the value between 0 and 1 half, the one on the right. F of 0, its width is 1 half, plus between 1 half and 1 is on the right. Whoops, that should be f of 1 half, sorry. There we go. Right, 1 half is on the right. F of 1 times a half plus 3 half is on the right this time, times a half plus f of 2 times 1 half. Now again, I would highly encourage you not to factor out the 1 half. Besides, we don't really ever simplify these anyways. The value at 1 half, we already got that. Remember, we're looking at the function here. This is y equals x squared plus 1. So that was 1/4 plus 1, or 5/4, plus a half. The value at 1, we knew that was 2 times a half. Plus the value at 3 halves, remember this is now 9/4 plus 1, or 13/4 times a half. Plus the value at 2, which becomes now 5 times 1 half. And again, you can leave this alone. Just leave it alone. There's our answer right there. AP says, don't worry about simplifying. But if you need to, this is just going to become 23/4. Now in this case, easy to look at, this is going to be an overestimate. So why would this be an overestimate? Well, there are two things happening. One, we're taking a right-hand sum, and the function is increasing. Now this is very important. So let's notice. Let's review up here. Notice the fact that the function is increasing does not determine overestimate or underestimate. For area, concavity, remember we talked about that with approximation of the value will always be an underestimate. But when we're looking at the area, you also have to look at which side you're taking the area from. For a function that's increasing, the number on the right is always bigger than the number on the left. So because we're taking a right-hand sum and the function is increasing, this is an underestimate. Well, if we look at a function that is strictly increasing, any number on the left is always going to be less than the number on the right. Therefore, our area is going to be below what it should be. All right. The next we're going to take a look at is what we call the midpoint sum. And this is sometimes the harder one. We're going to pick the middle number. And this is a little bit tricky. We have to get more creative. We're going to pick the middle number. So again, there's 1, there's 1/2, there's 3/2. So what we're going to do now is we're going to pick a number. I'm still going to look at my rectangles here, 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 and here. There's my 4 little rectangles. But now I'm going to pick a number. Well, what's in between 0 and 1/2? 1/4. So we're going to find the height of the rectangle at 1/4. What's between 1/2 and 1? 3/4. So I'm going to find the height of the rectangle at 3/4. What's between 1 and 3/2? Just continue the pattern. That's going to be 5/4. And if you notice, this isn't either going to be an overestimate or an underestimate. We don't know enough to determine this one, because if you notice, part of our area is above, part of it's below. What's between 3/2 and 2? 7/4. So when we find the area, remember, each rectangle, be careful, is still 0 to 1/2. We're just using the number in the middle to get the height of that rectangle, our function's value. But the length of each base is still 1/2. So again, to get the area, it's still going to be f of x delta x. Very important to write this down. So to get our area, we're going to look at the value of the function in the 1/2, so 1/4 in the middle, is still 1/2 plus f of 3/4 times 1/2 plus f of 5/4 times 1/2 plus f of 7/4 times 1/2. And plugging these in, remember our function is this, x squared plus 1. Plugging them in, 1/4 squared is 1/16. Plus 1. And suddenly a miracle occurs, and you're going to get 37/8. Well, I'll let you guys do that one, okay? But it really is important. This is the most important step. Plus 1 here, plus 1 here, and then your answer is always worth 1 point. So these are worth like 3 points, and I'm going to give you a point for showing your rectangles. So a question like either of these methods is always going to be worth 4 points for us in here. All right. Let's see here. So we've graphed derivatives before, so let's just take a look at this. This is just kind of a quick thing to do. The graph of the derivative is shown, so f prime of x is shown. They're giving me some sort of initial condition, and what they want me to do is find out what the original function would look like. Well, my initial condition is 0, -3. I can just look over here. On the domain 0 to 2, I know that the slope is 2. So between 0 and 2, the slope is 2. Up 2 over 1, up 2 over 1. Now, very important, notice they have these open circles right here, which means it's not differentiable. On 2 to 3, what are they telling me the slope is? -1. So between 2 and 3, down 1, over 1. And on 3 to 4, they're telling me the slope is 1. Up 1 over 1. And that's like a possibility of what our graph would look like. Notice, we are differentiable, so we have corners right here, which should match up with the fact that this is not differentiable, that they're open circles right there. All right, go to video number 2. We'll take a look at some more examples. See you then.